This is my home-developed autonomous sub-250-gram airplane. It uses a 32U4 microcontroller with a whopping 28K of flash, as well as a 9-axis IMU and a cheap GPS module. I designed my own board to fit these on before designing anything else. It uses the same pin setup you might find on an RC receiver, allowing the computer to be swapped for a regular receiver for airframe testing. Speaking of airframes, here's what I came up with. It uses a precise P51 airfoil with no twist, cut out of an insulation foam with a homemade hot wire setup. The first prototypes were based off of a plank design, but I switched to a swept wing as the plank's protruding nose section, bearing the largest load, broke off on about every flight. Swept flying wings allow for the entire fuselage to be reinforced by the wings. Every landing with this plane is going to be an outfield, no-gear landing, so the skin of the foam aircraft was protected by some 1.5 mil lamination. This airframe's first priority was to take a beating, as software was also going to be developed at home. The software for this project started by unpowered hand launches with some PIDs to control pitch and roll. The inputs were solely accelerometer at the time. Simply detect gravity and keep yourself perpendicular to it. This plan fell apart when electric propulsion was introduced, as the plane had no way of figuring out if acceleration was due to gravity or propulsion. So the gyroscope component was introduced, and a simple complementary filter to mix the inputs, and I was shocked by the improvement. It still had some glaring issues when it came to rotation around the yaw axis, but that's fine, right? I got surprisingly far with the simple setup, but after a few stalls it should have easily recovered from, it became very clear that the plane did not know its true attitude. I was using a 2D representation of my attitude when I later learned I should be using a 4D representation called a quaternion. So I took a couple days to truly grasp this concept. I have the Indian government to thank the most for this project, as they bring the best professors in the world to come teach a semester in India and publish everything for free online. It just so happens that virtual reality hardware uses this exact 4D unit vector to solve my exact same problem. Finally, it all makes sense. Now to write the code. But wait, there's got to be a library for this, right? Yeah, there totally was. The problem was satisfying to learn about, but debugging my own code when somebody else has free working code is not so satisfying. The final major component was navigation, which was surprisingly easy when you're in an airplane with a global positioning system. All I had to do was compute the error between my current heading and my target heading and just roll accordingly, plus stay in the air without going too high or too low. All of this code culminated in a total of 28,648 bytes used out of a 28,674 available. It was a tight squeeze. It can only hold about 8 waypoints, which have to be entered in the code and compiled to be used. There are some tricks I use to keep the flash demand down. The altitude PID function isn't a PID at all. It's just a proportional function with some bias to go above the set altitude. It removes any need for a variable offset that could cause oscillations. Heading control doesn't even have a function. It's just a heading error plugged straight into the roll with a 20-degree limit. Overall mission profile is based on timers and target distance. If the plane doesn't reach the waypoint in the set amount of time, it will force a landing. This is an easy way to ensure the unmanned aircraft will never encounter a failure mode where it flies off forever. After all, there's no manual override switch or even data logging. There's not enough flash storage to do that. A little extra information about the mission profile and the takeoff specifically. In the videos you might notice that the throttle and climb ends abruptly for a couple seconds and then comes back. This is due to filter saturation. The high acceleration on launch tends to confuse the filter, so to recalibrate the system for cruising level flight, the plane simply cuts throttle to about 1/3 and rides a stall for a couple seconds. This simple solution came after many rather abrupt full throttle landings. The last failure, the most catastrophic of them all, came right after the first successful field circumnavigation. Large control surfaces allow for excellent slow-speed control, but at high speed it tended to over-control. A pitch oscillation would begin, and no amount of derivative tweaking seemed to help. Simple solution. Make the control surfaces smaller. I never encountered another oscillation. Finally, some specs for those who are interested. It runs on a 2S Lion paired with a 20 amp ESC, running an EMAX 4100 kV eco motor, pushing a 4-inch 2-blade quadcopter propeller. This resulted in 30 to 35-minute flight times using an RC receiver. I'll put links to many of the parts in the description, as well as the code for any of those who would like to take a peek. I learned so many lessons with this project, and that's what made it a blast. Thanks for watching.
Uh-oh. Holy. Well, there goes it.